This is a 3 two-way valve, manual operated with the DEC in it. So this is the one with the selector switch on it, right? Okay. One of them. I think we got two. We only got one, and this is it.
What left is it? Four?
This is 3. We just went over 1 and 2 last time, right? Did we? Or we go over 3? This is a 5 two-way valve with it's pilot operated. Everybody okay there? Yes or no? Huh? That's a 5 two-way valve, pilot operated, spring return. There's the spring. There's the pilot. Now the actual symbol, the software that we draw this with it's called Visio, and they don't exactly draw the pilot valve exactly right. The pilot valve should have a rectangle around it, the true symbol for a rectangle. If we look at the prints for the for one of our lines over there, either Festo or the Amatro. We'll use look at the Amatro line. Nope. So they don't have any pilot operated. Who has pilot operated? None of them, all of them over there are solenoid operated. But if you look on the last chapter, when it gives you all those symbols for the operator, then it should be inside a rectangle. Everybody okay? But Visio, the software that we draw this with, doesn't have that option. And this is what they're doing. So I can't draw on this. Y'all okay? Y'all know what I'm talking about? Yes or no? Are we okay?
I just use that software to draw.
Yeah. We got another software I'm going to install on my computer. It's called FluidSim, where you actually actuate the valve. So that animation that I made by cutting and pasting and using Paint, that was made with Microsoft Paint. It actually does that, which is pretty neat. I'll try to get that on my computer and see if that way you can actually see the valve shifts. But it's good, and then again, it's bad. And why is it bad? Because you expect to see that, but in the diagram, those suckers don't shift. You got to do what? You got to imagine them shift. You got to picture that in your head. So this is so what's going to happen, of course, is in this position right here, the pressure is going to be locked off. It comes up here. It's going to go through port 1 out to port 2, and it's going to cause what to happen? The cylinder is going to retract. Right? So that I can't draw on it. I can follow it this way. So here we go. Right? So this guy here is in this position. Pressure's blocked off from here, so it can't flow through there. This guy's not going to shift. So he's just going to go out 1, going to come in 1, out 2, and then it's going to retract. Did I say, Steve? It's going to retract. Are we okay? When I come in here and flip that switch over, this is going to move over. Now 1 is going to flow up through here. It's going to flow out 2. And the pilot valve is going to come over and shift the thing over to the left. So pressure is going to come up here now, go through here, go up here, going to push my double acting cylinder. It's going to cause it to extend. That's a double acting cylinder with it's got a magnetic piston on it, double cushion, double variable cushion. We've already talked about that, right? Yes or no? Huh? So, huh? Yeah, but that's what that symbol is. It's variable cushion. What does the cushion do? Yeah, and we have what they call I think you asked about rubber things inside there. Those are not considered, those are bumpers, I'm sorry. So some of your cylinders have bumpers in them, and that's basically just a rubber pad on your head and on your cap. The head is what we call the side of the cylinder where the rod comes out. The cap is what we call the guy that's away from the rod. So what they do inside the cylinder, some of them have bumpers. You can buy them with bumpers. Bumpers just means there's a rubber cushion inside there to keep it.
The cushion is air, right?
No, well, yes, it's fluid. So in this situation, it is, yeah, it is fluid. So I think I've drawn this before, but we can look it up on the internet. Of course, well, I love the internet. Ain't nothing up there you can't find. So some of it's wrong, but you've got some good. We could say hydraulic, but we'll say pneumatic since that's what we're doing. And then we'll just come up here and see if there's any images. I guess we should say cutaway. There's a cutaway right there. So this is it, guys. That's it right there. Oh, let me get that one up by itself. So what we have is we have these guys right here that barely fit into these holes right there. Now this is going to be with an adjustable cushion. So what I have right here is I have a needle valve. And one of the advantages of the needle valve is we can precisely control the flow. So there's fluid inside this thing right here. So when this thing comes back in here, it gets into this thing right here. Now that fluid has nowhere to go except where? Out this little thing right here, back, and then to get back into the chamber. So what's that going to do is that sucker's going to fly back there, and it's going to do what? It's going to slow down. So a bumper is a bumper. It's actually going to do what? Beat against it. This guy is literally going to do what? It's going to go flying back there, and right before it gets, it's going to slow down and come to a stop. Fixed cushions, you have no control. Variable cushions, though, you got that little needle valve in there where you can control the flow, how fast it flows through there, and you can control how much it slows down. So you can make it beat up against the end a little bit because it's still got a very small orifice to get through. But you can control how much it decelerates right at the end. And these are called cushions.
When you say fluid, what you referring to?
Fluid.
So it's something other than air.
Fluid. So cushions are in cushions are in hydraulic systems,
right,
and they're in pneumatic systems.
In pneumatic system, I'm asking is it air or is it some other fluid?
In the pneumatic system, it's going to be a gas. Now the predominant gas is air. So when you say is it going to be something else, is it going to be? It could be something else. The only difference between a hydraulic cylinder and a pneumatic cylinder is what? No, what's the difference between the cylinders? The hydraulic cylinders are trying to maintain a liquid, so that means they got to be really sealed up real good, and we're going to be dealing with a lot more pressure. So that means all your seals are going to be your wipers that clean off. So normally we have what they call wipers up in here that actually ride on the rod. So when the rod comes in, if it's got any contaminants in it, it don't get into the fluid. And all that's the only difference. As far as the operation of them, they operate exactly the same. The cushions operate exactly the same. It's just that one is going to be probably made out of steel. The other one might be made out of plastic. Right, you understand? So the cylinders our Festo line make over there, they work fine. They're made out of plastic. So pneumatics can be made out of plastic. We didn't actually make them, but we talked about it. My son for Halloween wanted to put a cylinder in the ground, and then when somebody came up, it would shoot a skeleton up out of the ground, out of the coffin. We had it all planned out. We're just gonna make it out of PVC pipe. It's not great because it don't have to do very much pressure, right? Just keep a compressor out there. Have just a regular. We was going to use a ball valve that you go out and buy. You can buy them at Lowe's. Most people cut water off and on. He's going to put that thing. Of course, it never came to. Yeah, he made a. No, it just did. He works. He's a fire medic, so he's a medic and a fireman. And then he also is works for RPS ambulance. Yes, I know he's got a title. And then he teaches CPR classes. So you don't have any time for that anymore. But him and another guy, he's a sheriff. They built a coffin car one time. It was beautiful. The coffin had the steering wheel, had one of these. I think they got everything basically donated and they sold it somewhere for like $5,000. It was a coffin car. Had tail lights on it, headlights on it, had a radio in it. This guy, you should see this. But the coffin was donated. The guy donated an old golf cart they had with all the batteries, and they built it on that chassis. Good. I wish I'd have took some pictures of that thing. But no, he got so dang busy. He's so busy now he don't have time to do that stuff. But he used to be one of these guys that really decorated for Halloween. You know, the fake cemetery and ghosts floating around and all that. Now, how did we get off on that? You didn't do that to me again, did you? Franklin, you do that to me. You have a tendency to try to get me off task up here.
I didn't think you were going to go that deep. Real quick.
I always go deep. I always go that. Just like power, and me and transmitting power. So we okay. So that's everybody okay with the operation of this. Y'all got any questions on this? Pretty straightforward, right? Okay. We're gonna add our e-stop valve down at the bottom though on all ones. What's the pressure running? 50. You put 80 on one of this thing. Okay, so let's look at 4. Let's see what 4 is going to do. I think 4 is where we actually start adding speed control. So what type of valve do we use to control speed? Nobody knows. So what determines the speed? What of a fluid determines the speed? Well, let's think about that formula. The speed was 231 times the gallons per minute divided by the area.
So how fast the
Fluid flow. So how fast the fluid flow determines the speed, right? Y'all understand that? So it's how fast the fluid flows. And so, and how much, what's the bore you're pushing against, right, to get it to move. Hydraulics is really neat because the fluid don't try to uncompress on you when things start moving. Well, no. What are we trying to control? We're trying to control the flow. So what would the valves be called? Flow. What are we trying to control? We're trying to control the flow. So what would the valves be called? Flow. They're called flow control valves. Okay. And they're needle valves, but we have a symbol for them. We come over here, and the symbol would be, we've talked about this, but I don't think I remember it. So the symbol would be this. So we draw the line that we want to control the flow in. And then we come over here and we put two little things like that. That's basically an orifice. And then we come over here and put an arrow through it. So that would be a fixed flow control valve, which means you have no control. You buy it for a certain flow. The ones we have are like this. So what does that mean? They're variable. They're variable flow control. Now the problem is if we're trying to control the flow on a double acting cylinder, then we're going to have problems, right? You understand? And why is that? Why am I going to have problems if we're going to try to control the flow on a cylinder like this? If I want it to retract and send at the same speed. Well, it's going to try to retract faster than it's going to extend. So normally what we do is we put flow control on both sides. But the problem is that we don't want to control the exhaust. We want to control the flow, or vice versa, right? Now, on what we do on pneumatics is we control the exhaust. Everybody know why we talk about that. Yeah, so as soon, yeah, so what we do is instead of controlling the pressure, we control the back pressure. Does that make sense? Because what happens on pneumatics, as soon as the cylinder moves, the air would uncompress. And then it would have to compress. So it would be real jerky. But if we always make that cylinder work against something, if we don't let the exhaust out, we control the flow of the exhaust, then the cylinder is going to be smooth, right? You understand? Does that make sense? Because you always got pressure pushing against that thing. So that means if you got pressure pushing back this way, then the air is not going to uncompress because it's always pushing against it. So what we need to do is we want to control the flow coming out of it, but we don't want to control the flow going in. That makes sense. So what we do is we come in here and we'll put a check valve in parallel with it. Now the problem is we got two ways we can hook that check valve up. We can come up here and hook it in this direction, or we can come over here and hook it in this direction. So we do this so often that they make a unit. It's called a one-way flow control valve. So this is what we got. We have one-way flow control valve. I mean, they've got the check valve built into it. Okay. So if I'm going to control the speed, what we would do is this is this guy. I don't want to control the speed coming in. I want to control the speed coming out. So what we would do is we're going to have this, right? This is going to be adjustable. And on this side, what do we want? We want a check valve. So I'm going to point the check valve in this direction. And what I'm going to do is I'm going to point the check valve in this direction. And then my flow control, we usually draw the check valve. We draw the check valve over to the side. I wonder if let me erase that. There you go. So we usually draw the exhaust pipe. We draw it down, we put our flow control, and then we put our check valve over. And this would be inside a unit. So usually if it's inside one unit, they'll put these little dashed lines across it indicating, because you can do this manually, but like I said, one-way flow controls have been around so long that you could buy the unit themselves. But they'll put that dashed line around it indicating it's in one unit. So here we come up here, I'm going to try to make it extend. So what we do is our flow control, it would come up here, and which way would it go? Go this way, go up through there, go up through here. Here comes my exhaust. What's my exhaust going to do? This is going to block it, so my exhaust has got to go through the flow control. So what we're doing is we're controlling the exhaust, right? You understand? And we do that on pneumatics because if we didn't do that, our cylinders would be what? Junk. And plus, if we try to do a negative load, what would happen? It would just fall because the air wants to uncompress anyway, and it would just do what? It would just jerk that cylinder right out of it. Like I said the other night, hydraulics we could do it, but if you got any leaks in your hydraulic on your pressure side, it would suck air bubbles in there, right? You understand? And we call this meter out because we're metering the exhaust. We're metering the exhaust coming out of the cylinder, right? You can tell right off the bat when you look at your check, look at the arrows on the check valve. They're not pointing toward the cylinder, they're pointing what? Away. So if you look at it and they're pointing away from the cylinder, it means you're meter outing. If they're pointing toward the cylinder, it means you what? Meter in. Single cylinders, though, we have to meter because we don't have control of the other exhaust, right? You understand? So this is the way we control the speed. So now I can make it retract and extend at the same speed. I can make it retract faster than it extends, or I can make it extend faster than it retracts, because now I'm controlling both sides, right? So normally when we control the speed of a cylinder, we do it on both sides, because your extend and retract speeds would be different, right? You understand? But a lot of times we want them to be different. A lot of times if I'm pushing something this way, and then I'm bringing it back and I want another unit to slide in there, we want it to retract a lot fast and do what? Extend slow. But this way we can do what? Whether it's pneumatics or hydraulics, we can do it. On double acting cylinders, what did I say the term, what do people say? When in doubt? Meter out. Because meter out works on hydraulics and it works on pneumatics. But pneumatics, we very seldom meter in unless it's a single acting cylinder. Because if it's a single acting cylinder, we get control of the exhaust when it's retracting, but we don't get control of the exhaust when it's extending, because when it's extending, it comes out of a little hole in the cylinder, right? Understand that? So the only option we got on the single acting cylinder is meter in. Now sometimes you'll see them use these in tandem with each other. So one of them be meter out, one of them be meter in, and they'll put two of them in series, and that way you can control a single acting cylinder in both directions. You understand what I'm saying? So sometimes you'll see that on a single acting fluid cylinder, they'll have two flow control, they'll have two one-way flow control valves, but one of the check valves will be what? Meter out, and one of them will be set for meter in. So that means when it's extending, it would bypass one and go through the other. When it's retracting, it would bypass the other and go through the other. So you'll see that done sometimes. So this is the way we do flow control. Normally on a double acting cylinder, we use two. If we're trying to retract real fast, we might just use one of them on one side, right? On the extend side. We'll put one on the exhaust side for the extend. We wouldn't have one on the exhaust side for the retract. And we also have, guys, what we call a quick exhaust valve. The problem with these guys is if you're exhausting through a valve, then what do you have to do? You have to run that pipe all the way back to the valve. What's the odds of the valve being mounted up by the cylinder where we're at? Very unlikely, right? You understand? And the further you have to run through the tubing, what happens when we put flow through a tube? It's just like when we put current through a conductor, we have what we call line loss. So we have loss in there. So they'll put a quick exhaust valve. It's just a little tiny valve. I'll show y'all that, but it's mounted right by the cylinder. And what it does is when it exhausts, it'll go through that thing. And pressure, and we use those on single acting cylinders a lot too. Or these guys that we want to exhaust on double acting cylinders that we want to exhaust real fast. So we have those, over there. But that's what this lab is. I know we need to go to lab, guys, so we won't talk about the other circuit, but let's look at this one. That's not it, Rich. What's that? That's not it, Rich. I must have closed it out. No, that's the PowerPoint, right? Fluid power, valves, pneumatic valves. No, this is not the one. I thought it was this level. So how's this level gonna work? Y'all know what this is the symbol for? By the way, and this is one thing that Visio don't do either that you're supposed to do. If you look at the symbols for fluid power, every time you have a connection, you're supposed to have a what? A dot. You know, I always told to do that. So Visio don't do that for us. So I need to pull these back off and put those dots there. What's this guy right here? This is a DNA. They don't show us. So this is one of our selector switches. This is a double acting cylinder. They're not using the right symbol. But then this right here is a cam operated valve. Right. So what's this guy going to do? So I'm gonna come over here and flip my switch. So right now it's set up, according to this one, it's set up to extend. But if it extends, it's gonna come out there and hit that cam operated valve. That's gonna shift it over. It's gonna cause the what? The single acting cylinder to extend. When you retract the double, when you flip your D10 to the other position, the double acting cylinder is going to retract and it's gonna cause your single acting cylinder. Not do that. I can do it. So what we got is in electronics we call these limits. So these are basically electrical switches that something mechanical comes up and hits that, and it causes it to shift position. Well, in pneumatics we have these cam operating switches. So basically you go over there and look at yours, it looks like a limit switch. So it's got this little wiper coming out on the side, you know, and it's got a rotor on it. Well, what's going to happen is we're going to use our manual valve. This is moving toward what we would run into automation. So one of the guys last semester he set up a system where you come over here and you turn that thing on, and you have two actuators that just sit there. So it was automated, right? Well, how did he do that? Well, he did this with these cam valves. So what he did is he put that valve, he put a cam valve up on that one, which controlled the single acting cylinder. Then he put a cam valve on the single acting cylinder that changed the direction of the dual acting cylinder, double acting cylinder. So when you put that switch down there, that sucker just sat there and did what? Back and forth, and he put a counter on there too, so it did like 5 times. And that was his troubleshooting. Everybody thought that was cool. And you always have somebody that does something, try to do something with things. But so what we're doing here is that you are not controlling that single acting cylinder. You're controlling the double acting cylinder. When you hit that double acting cylinder, it extends and hits that cam valve and causes it to change direction. When it changes direction, that's what causes the single acting cylinder to extend. So you're controlling it indirectly, right? Does that make sense? So it'd be like, you know, in electricity, this would be what we call a limit switch. But basically, when something comes out there and hits it, it'll either open or close the switch, and then you would cause something to happen. We use these all the time, like on milling machines. That's going back and forth and back and forth, back and forth. All the controls that going back and forth is just limit switch. And I come here and start the thing and just go back and forth, back and forth, back and forth. So we have these we don't have any pneumatic switches like that over on the line, but we got limit switches. And they do exactly the same thing. So we got a motor that comes up here and runs, and when it gets to where it's supposed to be, it stops. So, but that's automation. So, we got 2 of these over there, I think. We got 2 of these cam operated switches with roller cam. They're called roller cam operated switches because they actually got a rotor on them. No inventory. Don't you ever see them? I think I've got 2 of them. So the flow control must be the next slide. This is all we have time to go over. 'Cause. 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 'C So if you got any questions, this is when you need to ask them, right?
I do have a question. I know this is probably pretty well addressed last time. I know we're gonna write on the back of operation. Well, are we drawing a line diagram or a line? Are we drawing the diagram?
Not on lab 1, not on lab 2. I think we do our first design on lab 4 or 5.
So it's
When
just,
you get-
we just need the directions on how to operate.
Right. Well, pretty soon, you can see these circuits are not complicated. You're getting into like designing an amplifier circuit. You know, electrical control circuits and pneumatic control circuits are fairly straightforward on how to design them. So when they came out with programmable logic controllers, the main language we program it is the same, is what we call ladder logic, which is basically the same thing we use in electrical. So once you understand these basic little circuits, it's a lot simpler on designing it. You get into designing amplifier circuits or communication systems. You know, you get into some really heavy math. If y'all take solid state or even AC, take AC. You ever had AC yet? You ever plan on taking? It's not an easy course, is it? And people don't understand how much there is to AC. People think that AC and DC is the same. They're not. And the problem you got is that you don't understand the way things, you might not ever use that math again, but if you understand it, then you understand why things are what they are. So if I looked at this ballast on this fluorescent light, it's got 2 wattage ratings on it. Why? Right? Why? Well, in AC, you'll understand why. You'll understand why we have 2 wattage ratings, why we have what we call apparent power and true power or real power. You understand why elemental power does what they do. You understand why these people have to do what they do. You understand where the efficiency of these AC motors come into play. You understand phase shifts and stuff like that. So what happens in an AC circuit is the current and the voltage can get out of phase with each other, which means they're not occurring at the same time. So when your maximum voltage is in the circuit, you're not getting maximum current. And when your maximum voltage starts dropping down, your current comes up. If you have inductors or capacitors, and it's really weird. So that's why you learn why things are the way they are. So anyway, let's go to lab.